There we go. And then it is my pleasure to introduce my PhD brother, actually, Ayberk Tosun, currently at Zeroth Research, who will talk to us about constructive and predicative locale theory in univalent foundations. Please, Ayberk.
Okay, thank you very much for the introduction, and thanks for the invitation. It's great to be giving a talk at HoTT. So I will be talking about my PhD work with Martín Escardó on the development of locale theory in the constructive and predicative foundational setting of HoTT. I will first present the groundwork we did for the development for such a constructive and predicative development. And then I will present the use of this framework to develop the following results from locale theory. So the constructive and predicative versions of the following: stone duality for spectral locales, the so-called patch locale of a spectral locale that transforms a spectral locale into a stone one, and then some applications to the point-free topology of Scott domains. Okay, so if you don't know what a locale is, let me give you a brief summary. So a locale is a notion of space that's defined solely by its lattice of opens. In point set topology, these lattices of opens are required to be the subsets of some set of points, but in point-free topology, no such stipulation is made. So we take the lattice of opens as an abstract lattice, and we try to do topology with this abstract algebraic lattice of opens. That's the fundamental idea. And locale theory is quite important for constructive mathematics in that it usually has deep ties with constructive mathematics. And a good example of this is the Tikhonov theorem, whose point set manifestation is equivalent to the axiom of choice, whereas its point-free manifestation is constructively provable. So by going from point set topology to point-free topology, we can not just avoid the axiom of choice, but we can in fact do it constructively, the proof constructive. And this, this clarifies the content of the Tikhonov theorem. We can make constructive sense out of it in this sense. And our motivation is as follows. So HoTT is constructive and predicative by default, because once we are working with HProp, we have the question of how to resize HProp arises, and if we don't want to use propositional resizing, we need to work predicatively. And despite these difficulties, it seems to be working quite well in practice, because with this we get HITs, which allow us to circumvent impredicativity in many cases. And it addresses shortcomings of type theory as a foundational language for constructive mathematics. So what we want to do is we want to test HoTT as a foundational setting for constructive mathematics by trying to do as much of this as much of locale theory as possible, which is an important piece of constructive mathematics. That's the idea. So let me start by pinning down some foundational preliminaries. So I will talk about the smallness of a type, by which I mean, so given a type X in universe U, it is called V small if it has a copy in universe V. So sigma y X is equivalent to y. And you might be wondering if this is a proposition. And if you have that question, keep that in mind, and we'll come back to that. And then I will also talk about local smallness, which is to say that the identity type is V small. So we say that the type X in U is locally V small if the identity type x identity type between x and y is v small for every pair of inhabitants. And by omega u, we denote the type of propositions in a given universe u. And now I state the propositional resizing axioms that I mentioned. So the propositional UV resizing axiom says that every proposition P in universe U is V small. A stronger form of this is omega UV resizing, which says that the entire type omega U in universe U can be, it has a copy in universe V. And then there is also omega not resizing, which says that the type of not stable propositions can be resized in this way. And I'm guessing most people are familiar with this, but let me note that classicality implies impredicativity automatically, because if we have the law of excluded middle, it says that omega u is just 2, which can then be easily resized into every universe. So we need, if we want to investigate predicative mathematics, we need to be doing constructive mathematics. And in this sense, it's a branch of constructive mathematics. Okay, so going back to the question regarding the propositionality of the notion of being small. This is a proposition, but the fact that it's a proposition uses univalence. So this was shown by, I think first by Martin in type topology. It was written down that for every type A in universe U, for every pair of universes U and V, the type expressing that A is V small is a proposition if and only if the univalence axiom holds. So this has direct connection to univalence. I mean, it is univalence. And also some terminological remarks. So in this talk, I will say there is some for unspecified existence. For specified existence, I will say there is a chosen or specified. I don't use the term mere existence. And sometimes if extra clarity is needed, I will say there is an unspecified. Okay, and one final thing before I move on to point-free topology. At some points of our investigation of locale theory, we also use the set replacement axiom, whose statement is the following. So given a function from a function f from x into y, if y is a set and x is u small and y is locally v small, then we know that the type image of f is u least upper bound v small. And for us, the interesting special case is the following. Given a function f from x into y, where y is a large set, to show that its image is u small, it just suffices to show that y is locally u small. And Tom de Jong showed that this is equivalent to the existence of small set quotients. So we can write it down as an HIT. I mean, in our work, we want to be careful regarding which HITs we use, but for many people, it's fine to assume these HITs. So yeah, we will be using set replacement in some places. Okay. Okay, so now let's start talking about locales. So my notation for families with index types living in universe W is fam sub WA. I will also talk about subfamilies, which is the composition with a family on the index set. And a family is called directed when the type X in consideration is a preorder. It's called directed if the index type is inhabited, and for every pair of indices I and j, they have an upper bound. they are there is an upper bound in the family. Okay, and I will also work with Krotowski. So in constructive mathematics, there are different notions of finiteness, and the one we will be interested in is Krotowski finite, which says that a type X is Krotowski finite if there is a surjection from the finite type, the type with exactly n inhabitants, into X for some natural number n, and then a subset is called Krotowski finite if the subtype it gives is Krotowski finite. Okay, I think that's enough preparation. Now I give you the definition of a locale, which is defined using frames. So this definition is parameterized by three universes, U, V, and W. U is for the carrier set of the frame, so type A, and the partial order on the type, which has truth values in V, and then it has finite meets given by a top element, a binary meet operation, and then a join operation over W families. And this is also required to satisfy distributivity. Sethood is not a requirement because it follows from the partial order. And I will talk about large, locally small complete frames, by which I mean U plus U frames. So actually we won't be needing the generality, the universe generality involved in this definition, but I'm writing it down now just to be able to explain why we won't be needing it. Okay, and to make things a bit more concrete, let me give an example right away. So if we have a small set A in universe U, we take its subsets, which form large, locally small, and small complete frame when ordered under inclusion with subset intersection and union. Okay, so this is large, locally small, and small complete. And to find the right category of frames that we should work with, that investigation of constructive and predicative locale theory should focus on, we need to also look at some foundational results. So in predicative mathematics, it is known that certain classes of non-trivial complete lattices cannot be constructed, and this was first shown by Giovanni Curie. And this is by a meta-theoretic argument using the generalized uniformity principle. And Jong and Escardó gave a much more direct version of this result by deriving directly a form of resizing from the existence of a non-trivial complete lattice. And for us, this has the implication that if there exists a non-trivial small frame, then omega resizing holds, which we know to be independent. So if we want to investigate locale theory in this predicative foundational setting, we need to focus on large and small complete frames. Okay, and we know this precisely by this theorem. And in addition to this, we require local smallness, and that's because most of the locales that come up in practice tend to be locally small, and most things work fine with locally small frames. And by frame U, I denote the category of such frames and frame homomorphisms, and the locale is defined as an object in the opposite category. And for variables ranging over locales, we use x, y, z, and for their opens, we use capital letters U and V. For continuous maps of locales, we use f from x to y, which is defined by a frame homomorphism from O of y to O of x, because even though we're working with algebraic things, we pretend that they are spaces because they have a different attitude when we switch to the opposite category. Okay. So I use the term locally small in two different contexts, which I haven't justified, and that is justified by the following. So for every u.w.w frame, if the order is if the truth value of the order is t small, then the set L is locally t small, and that's because when we have meets, the order is always equivalent to x meet y is equal to x, and that is something that is an identity type of this in U, so we can always resize that into U. So the order is at most U small. And when we're working with large things, we know that it is at most U plus small. And you might be thinking, can this not be even smaller than that? Maybe there is some clever trick that shows that it's even in U. And that cannot be the case because of the following counterexample. So if we consider a large set, X living in U plus, we can consider the power set frame on the large set. I'm cheating a bit here because I technically didn't define the power set frame on a large set, but it can be done. And then the power set frame on a large set is large and small complete, because we still have joins of small families. And if it is locally small, then we can do the following. We take the power set, we take a large proposition, P in U plus. We take the power set of P, so P of P, and then the entire set here being included in the empty set is equivalent to not P, which means not P is U small by local smallness, which means not P is U small. So this is an example of a frame that is large and small complete, but not locally small unless omega not resizing holds. But still, we focus on locally small things, and that's everything we will look at in this talk. But there are examples of things where we don't know if it's locally small, and this is like it's a non-trivial question. So let me give some more interesting examples of locales. So the terminal locale is given by the initial frame, which is h prop u itself. So again, we work in the category of locales, large, locally small, and small complete locales over some base universe u. And in that category, h prop u gives us the initial frame. Propositions are ordered under implication, and the implication is a small proposition, and it has finite meets and arbitrary joins, and we get the join completeness exactly from the unspecified existence operator. And this is the initial object in frame U, the terminal object in loc U. Okay. Here's a more interesting example. So a locale X is said to have the universal property of Sierpinski if it has a specified open such that for every locale Y and for every open, there is a unique map giving us that open. So in other words, this says that mapping into Sierpinski classifies the opens of locales in the sense that by mapping into Sierpinski, we get exactly the opens of the locale. And it is also just a reformulation of saying that this is the free frame on one generator. So it's freely generated by the unit type. And we construct this Sierpinski locale as follows. We take h prop u, we take Scott continuous maps on it, which are ordered under inclusion. And then this specified open u from the universal property is the map true that just says this is the true proposition. So it's the singleton set true proposition. And now going back to the question of local smallness. So this here we're working with a subframe of the power set frame over over a large set, omega u. So it's like the counterexample we gave. We take we take the power set frame over a large set. And this means that the inclusion order involves a quantification over the entirety of omega u, meaning it's not small a priori, but it can be shown to be small by because there's an equivalent version which just quantifies over the decidable propositions. It's defined as follows. We just quantify over the type 2. So beta here is the map sending 0 to bottom and 1 to top. And thanks to Scott continuity, these are equivalent because we can decompose a proposition P as the set of decidable propositions that are below it. And then by Scott continuity, we can push S into such a join, and that gives us local smallness. So local smallness is not, sometimes it can be non-trivial to prove, and it can be making use of the specific topological properties of the locale in consideration. Okay, so in locale theory, there are various ways to define, various equivalent ways to define the notion of sublocale, such as regular frame quotients and frame congruences, nuclei and fixed sets and so on. And here we will be working with nuclei. A nucleus on a locale X is a function J that is inflationary idempotent and preserves binary meets. Okay, now let me say a few more words on what is impredicative about locale theory. Because when I gave talks on my work in the past, I think this was the question that I mean, when I mentioned that I was working on predicative locale theory, I think the question that I got the most was, what is impredicative about locale theory? Because it's not obvious at first that there is impredicativity involved. And actually the answer is everything is impredicative about it. Like there are so many things that are impredicative about it. So, for example, in the traditional development of the subject, the fact that frames contain Heyting implications is quite important. So if I pick up stone spaces and look at an exercise which gives two easy examples of nuclei, I see that the open nucleus is defined as follows. So on an element of a frame, the open nucleus is the map sending something to A implies something, okay? And this corresponds to the open subspace of a locale. But we cannot define it because the existence of this Heyting implication comes from the adjoint functor theorem, which we know is satisfied by a complete lattice because we can take large joins by quantifying over everything in the lattice, which we cannot do here because that will be a large family and its join will not be available to us. And so more generally, right adjoints of frame homomorphisms, which are very essential in locale theory, are not available. And there are more things like arbitrary meets. So the meaning of complete lattice changes because we have meet completeness doesn't follow from join completeness. And for example, this definition of sublocale using fixed sets, this presupposes the existence of both arbitrary meets and Heyting implications. It's defined as a subset that is closed under arbitrary meets and under Heyting implications. Okay. So what do we do about this? We work with bases for locales, small bases for locales. So a family of opens is a base if for every open U, there is a specified directed small family on the base, giving the open as its join. And then we will also be interested in the weaker notion of base, where we use unspecified existence for this. And I will also use the term extensional if the base in consideration is an embedding. It's given by a family that's an embedding. And interesting classes of locales can be defined just by imposing some conditions on the base. And here are a couple of examples. The technical details here are not very important because I know that I haven't defined everything, but just to give you an idea. So, for example, spectral locale can be defined as a locale having an unspecified small base that consists of compact opens, contains the top open, and is closed under binary meets. Zero-dimensional locale can be defined as a locale having a small base that consists of clopens, and similar things for regular locales, locally compact locales. Stably locally compact can also be defined in a similar way. And this is a technique that usually gives rise to predicatively well-behaved definitions, and it has been used in Tom de Jong and Martín Escardó's investigation of domain theory in univalent foundations. And the inspiration here comes from the literature on locally presentable and locally accessible categories. We import these ideas into the Posettal setting. So we're working with Posettal categories because in a predicative setting, even though we are working with lattices, we are forced to work with such conditions of smallness. And using this, we can prove the Posettal adjoint functor theorem for frames, which tells us that every frame homomorphism has a right adjoint provided that there's an unspecified small weak base. So we get Heyting implications just because the meet map has a right adjoint. And now our framework for locale theory is complete because now we can also write down F lower star provided that we have a weak base. And we can start doing more interesting locale theory. And to give two examples, the terminal locale has as a base the map. So again, the decidable propositions. So the map beta sending 0 to bottom and 1 to top, because each proposition can be decomposed into the join of the decidable propositions below it. And then the Sierpinski locale, again, we work with the decidable propositions, but we take the principal filters on decidable propositions, which are scut open subsets. Okay, so the second question that I got the most about my work is how is this different from formal topology, or is this formal topology? Is this better than formal topology? Is this worse than formal topology, and so on? So I want to give a brief comparison with formal topological approach. So formal topology is the standard way of doing locale theory predicatively in the context of type theory. It was invented when Giovanni Sambin and Per Martin Löf were trying to do constructive point-free topology in type theory. And there, some notion of base is replaced with the notion of frame as a notion of space in itself. So this is a formal topology is something like a small set of generators equipped with a covering relation. And the frames they generate are always large, locally small, and small complete. So this is analogous to working with a specified intentional base. And it is like formal topology is quite useful for presenting locales, but then in the setting of univalent foundations, we need to be a bit careful, because when we're working, when we're replacing our notion of locale with something else, now we have some some extra structure, the base structure, and we're working directly with the base structure. So this is the difference of what we are doing to formal topology. We want to work directly with locales and see what can be done in that more extensional setting. And when the need arises, we introduce the notion of base. And in some cases, which I will now talk about, they arise naturally. Like the base arises quite naturally. Okay, now we come to compact and spectral locales. A compact locale is the standard definition in locale theory is this one. So we say that an open U of a locale X is compact if for every directed family of opens covering it, there is something in the family that it is below. And this corresponds exactly to the standard every cover has a finite subcover definition from topology, but with Krotowski finiteness. So it is equivalent to saying for every family of opens with U equal to this join, there's a Krotowski finite subfamily, and that subfamily gives U as its join. And then the locale is called compact if its top open is compact. So from the examples we looked at, the terminal locale and the Sierpinski locale is compact, but the discrete locale on the power set of natural numbers is not. Now, I will talk about a class of locales called spectral locales, and the motivation for that is as follows. So stone duality was first discovered in the context of stone spaces and Boolean algebras, and it was later generalized to the setting of spectral spaces and distributive lattices. This was in 1936 and 37. And the fundamental idea here is that a stone space arises as the space of ultrafilters of some Boolean algebra, and then the algebra of Clopens of such a space is always a Boolean algebra. But it's really the algebra of compact opens that's interesting. And in stone locales, the two coincide, but we can generalize from stone spaces to spectral spaces, where we take the we look at the algebra of compact opens, and given a distributive lattice, the prime filters of that distributive lattice gives us a spectral space. So it is a generalization of stone spaces. And if you look at the stone spaces book, for example, you will find a definition that looks like this. A locale is spectral if it is compact. Compact opens are closed under binary meets, and the compact opens form a base. And here, to translate this into univalent foundations, we additionally stipulate that the type of compact opens is also small. So this condition SP4 here is a further requirement. And then a spectral map is a map of locales that reflects compact opens. So this is the category of spectral locales is defined as spectral locales as objects and spectral maps as morphisms. And univalence, assuming univalence, this definition is a property, because we know that. So we know that this is proposition because we're using the notion of weak base, and then we know that being small is a property, as I mentioned in the introduction. But so yeah, the univalence seems to be required to express this property of being spectral. And so in the introduction, I gave a definition of spectrality as a special case of this of this technique of imposing a small base to satisfy certain conditions. But so I really gave two definitions of spectrality, and I haven't yet justified their equivalence. So this definition, which I marked double dagger, and the previous one was dagger. So it is quite a reasonable requirement for a candidate notion of spectrality that it satisfies stone duality. And this definition does satisfy stone duality, but to be a property, it seems to require univalence. Whereas the other one is it uses truncation, so it is a property without univalence. But then to show that it enjoys stone duality, it seems like we need to go to this definition. So and to go to this definition, we need the propositionality of this definition. So it really seems like univalence is helping us here to express this property in a natural way, in the way that that clearly satisfies stone duality. Okay. So to explain the technical details of this a bit more, so by spectral base structure, I denote what I said before, a base satisfying these conditions, and I call this a spectral base. And the first definition I gave was the truncation of the spectral base structure. And it can be shown that whenever we have a base consisting of compact opens, the image is equivalent to the type of compact opens. And if we're also assuming set replacement, then and the base is small, then we know that the type of compact opens is small because we know that the image of the base is small. And so this gives us the following. Assuming univalence and set replacement, whenever we have an unspecified intentional spectral small base, from that we can obtain a specified extensional spectral small base. And in other words, this has split support in the terminology of this notions of anonymous existence paper by Krauss, Escardó, Kokan, and Altenkirch. So just the mere existence of the spectral base gives us the actual base. And this goes through the fact that the compact opens form a weak base, whose propositionality requires univalence. And from that we get the spectral base structure. So for those who might be familiar with Tom de Jong's PhD thesis, there algebraic DCPOs are also considered, and there is this result that you can get structural algebraicity from a DCPO that is equipped with a small compact basis. But this, I mean, the proof of this also applies to algebraic DCPOs, and it gives that you get something structurally algebraic even if you have the mere existence of the basis. And this seems to be actually helpful in stone duality. Okay, so how am I doing on time? I have around 20 minutes left. So now let me quickly present stone duality in this predicative setting. So a small distributive lattice over the base universe U has a meet operation, join operation, binary meet operation, join operation, and these satisfy associativity, commutativity, unitality, idempotence, and absorption. So we don't work with an order here. We directly work with the meets and joins because we're working with something small. So it's the order we get is automatically small. And by d lat u, I denote the category of small distributive lattices. And oh, by the way, I learned last week, due to a result by David Verne, that the sethood condition is not essential here either. And I think this is much less obvious than the one for partial orders. And a small ideal of a small distributive lattice is a subset that is inhabitant downward closed and closed under binary joins. And when we have locale, spectral locale, that is spectral in the sense of double dagger, we take the type of compact opens, we get a small distributive lattice, and it is small because we required it to be small. And these two maps, K and spec, so taking the small distributive lattice of compact opens and taking the spectrum of a distributive lattice through the frame of ideals, it gives us an equivalence of categories. And by using the structure identity principle in these categories, we can also turn it into a type equivalence. And to clarify the relationship, so the patch locale construction clarifies the relationship between the category of stone locales and the category of spectral locales. So a stone locale is one that is compact and zero-dimensional. I didn't define the notion of clopen previously, so a clopen is an element of a frame that has a Boolean complement. And as I mentioned previously, in stone locales, the clopens and the compact opens coincide. And every stone locale is spectral. And in the other direction, we can universally transform spectral locales into stone ones. And that is the right adjoint to this inclusion of stone locales into spectral locales. And we also developed this in HoTT, and it has been completely formalized in Agda. And for that, we used Martin's description of the patch frame as the frame of Scott continuous nuclei on a given frame. And there is an interesting question here, because Martin's previous work uses the fact that the frame of Scott continuous nuclei is a subframe of the frame of all nuclei. And in this predicative foundational setting, we don't know if the frame of all nuclei can be constructed. Actually, we don't know many things about it. We don't even know if it's locally small. We don't know if it has a small base and so on. And there are several constructions that we know of, so by Banaszewski and Wilson and Simmons and so on, and they all seem to use some kind of impredicativity. For example, Escardó's construction of the frame of all nuclei uses the Pataraya's fixed point theorem, the main lemma used in which was shown to imply a form of resizing by Tom and Martin. So there really seems to be something inherently impredicative about it. So we believe that if this lattice of this meet-semi-lattice of nuclei is joined complete, some form of propositional resizing should hold. Like there is some fundamental use of impredicativity going on in the construction. And in our construction of the patch frame directly, many technical things had to be reworked because of this problem that the frame of all nuclei isn't available. And I want to give some credit to my collaborator Igor Arieta, who solved one of the problems here when we were stuck in the construction of the patch frame. The details of this can be found in our paper, The Patch Topology in Univalent Foundations. Okay, so I have 15 minutes, which should be enough time to discuss the topology of algebraic DCPOs. So here is my version of the notion of algebraic DCPO in this foundational setting, which is like this double dagger definition of spectrality that I gave. So it's a bit different from the definition you will see in Tom's work, but it is equivalent due to the reasons I explained. So a directed complete partial order, again over some base universe U, is algebraic if the type of compact elements, or maybe I'll use the term finite element when I'm working with DCPOs for clarity. It forms a weak base, and this type is required to be small. And the Scott domain is a pointed algebraic DCPO that is bounded complete for or small families, and also satisfies this additional condition that upper boundedness of finite elements is decidable to make it constructively well behaved. And we take the Scott topology on this, which is subsets that are upward closed and are inaccessible by small directed families. So if the join of a small family is in S, then there is already something in the family that is in S. And this Scott open subset, well, this should be algebraic, I think, not for every DCPO, because local smallness requires algebraicity, so there is a typo here. For every algebraic DCPO, the Scott open subsets form a frame, and then for every Scott domain D, it can be shown that the Scott locale is spectral, and this is, I mean, it gives us a very rich class of examples of spectral locales to test this definition of spectrality with. And to give you an idea of the proof of spectrality, the base here, the small base, is the type of words over the type of finite elements of the domain. That's the index of our base, and then we take all unions of principal filters on the finite elements, and this base is spectral base. And in practice, it's usually easy to show spectrality by working with some intentional base and showing that it forms a spectral base. Okay. So conclusion. We wanted to do locale theory in univalent foundations, and we did quite a bit of locale theory predicatively. We did the patch construction, stone duality, and the point-free topology of Scott domains, which we also applied to some other things in constructive domain theory that I didn't have the time to talk about today. And univalence and set replacement helped our investigation in some places. And especially univalence, it seems to have played an important role, but I'm not making any claims to whether it's essential or not, because maybe there is some other clever definition of spectrality that avoids both of these problems that I mentioned. I don't know, but it's certainly a very natural thing to do, and it was the obvious thing to do when we wrote down this definition of spectrality and required the type of compact opens to be small. And all of this has been completely formalized in the AGDA as part of Martin's type topology library, and that is under the locale sub-development. And some further directions that I want to explore in the future. So I mentioned formal topology, which is very useful for presenting locales, and I haven't looked at too many interesting examples of locales, like the locale of real numbers and so on. And this is something I would like to do, to integrate more formal topology into this work and work on more, like construct some more interesting locales. So there is this problem with the constructing the product of two locales predicatively. So even for formal topologies, which are, as I said, like specified intentional small bases, this is an open problem, and this is the reference for this is the inductively generated formal topologies paper by Kokan, Sambin, Smith, and Valentini. And I think it doesn't seem to be possible, but no one has shown that it implies a form of resizing or something. So this needs to be investigated further. The problem with the frame of all nuclei that I mentioned, that it seemingly requires some form of impredicativity. We started investigating the patch of the scat topology on a scat domain D, which classically corresponds to the Lawson topology. But constructively, it's not the same thing. And yeah, this is something that I want to explore further. But when I was working on looking at the Lawson topology as a locale, it wasn't even locally small. So there was a problem of showing local smallness. I would like to explore that further. Extending this to stably locally compact locales is also another interesting direction. So this is locally compact locale is a locale whose frame is a continuous lattice, and then the stability condition says that these are closed under the way below relation. So it is a generalization of patch, and it has been done by Kokan and Zhang previously using formal topology, and I think in this setting it will also be possible, but it will be more difficult compared to our construction of patch. And also Priestley duality is known to work constructively. I guess I don't know if it will also work predicatively like stone duality does. So I think that's it. Thank you very much.
Okay, thank you very much. Let's have the usual silent applause for Ayberk. And let's open the floor for some questions. Is there anyone who wants to go first? If not, I'll go. So I have a couple of questions. So one of them is that you mentioned this very recent result by David Wern about the sethood of distributive lattices.
Yeah.
So I wonder if, I mean, this is a very sort of surprising and nice result, but my conjecture would be that it doesn't really have much practical value in your development, because the kind of distributive lattices that you're considering, it should be fairly trivial to prove that
Yeah,
they're sets. Would that be correct?
I guess not. Yeah.
Yeah.
I don't think it because all the distributive lattices, I mean, that I can think of are yeah, they are sets anyways. So
Right. Yeah. Yeah. Something similar
I mean,
happens
the
with
the
the.
carrier types are sets anyway. So it's like
Well, they must be sets, right? But you can show them to be sets easily anyway. Which
yeah.
is, yeah. I mean, something similar happens for the posets. I mean, you don't need the requirement, but it's always kind of trivial to show anyway. Um, so another question I had is, you mentioned this decidability condition
Scat
in
domains. Yeah.
Scott domains. Yeah, could you comment a little bit on
Let me
where
go back.
that gets used? Slide 42, I think.
Slide 42. So decidability of upper boundedness.
Yeah,
This gets used when, if I recall correctly, when proving the compactness that compact opens of the scat locale are closed under binary meets. So the condition for, so we want to show that the scat topology is spectral, and we have the compact opens in the scat locale, and to show that the meet of two compact opens two compact scatopens is compact. I think this condition gets used there. Does it get used anywhere else? I don't remember off the top of my head right now. Yeah, I need to read my PhD thesis again.
Right. Do you have any questions in the meantime? If not, I'll just keep going. Happy to give someone else an opportunity as well.
Yeah, I might ask a question.
Yeah,
Hi,
go
Ayberk.
ahead.
So for future work, you were quite modest about keeping it the scope within domain theory and topology and locale theory. But you could also try to be a bit broader and say, what about predicative sublattice theory more generally? So not just frames, but so actually you can develop locale theory from the point of view of sublattice theory, as Shayal and Tierney did in their paper on extension of Grothendieck-Galois theory. So that's one direction, just try to go towards sublattice theory. Have you thought about this? And the other thing is to raise the level of truncation to go to predicative topos theory. Do you know if anyone is doing that in type topology?
So regarding the theory of sublattices, no, I haven't really thought about that. It comes up in some places, like constructing the free frame, for example. For that, I think in sketches, this goes through the category of complete joint semi-lattices, for example. So maybe if I had the theory for that, it would simplify some things for me. But yeah, maybe this can go deeper. That's a good idea. So, and what was the other question? Oh, predicative topos theory.
Yeah, exactly. Yeah.
Yeah, I don't know about that. I'm yeah, it's not something that I thought much about, but it might be interesting.
That's all right. Thanks.
Any more
So
questions?
one question that I had previously in this direction, like regarding I mean the fact that topoi generalize frames, where the categorification of frames in a sense. So in my master's thesis, I worked with a notion of formal topology due to Terry Kokan, that he calls an interaction system. And there, so this is like so this is an what is called an index container, or a generalized W type, that gives us the cover of the formal topology, from which we get the opens of the frame that it presents. And there, when I was working on that, it seemed like interesting thing to something interesting to try, was to maybe in to categorify this inductive cover construction, because I mean, formal topology, it comes from I mean, it is an idea borrowed from topos theory, that we take Grothendieck topologies back into the posital setting. And that's one thing I can say about that in when we work with these more intentional notions of bases in formal topology. Some more interesting things come up, and can this be categorified? And to work with topoi, this I don't know, but that's something that I would be interested in hearing the answer to.
Okay. I have one comment actually. I think it was slide 27 where you compared to the formal topology
Yeah,
setting.
Mhm. And I wanted to talk more about that, so yeah, let's go back to that slide.
I just had a small comment that so I think it was Andre Bauer who told me actually, but one advantage that you have over you've gone too far back by the way.
Oops, sorry.
27.
27.
One advantage that you have over the formal topology setting is that you can work with functions, whereas in the formal topology setting you have to work with relations, and that can be a bit cumbersome. So I mean,
Functions, relations as,
well, so you want to go between two frames, and so then you could just look at frame homomorphisms.
right,
But
yeah.
if the only objects you consider are the formal topologies, then you have to consider a relational approach. So the
Right,
difference really is not so much on the object level, but
yeah.
once you
As a
go to the
morphism,
morphisms,
as a
yeah,
morphism of formal topologies, yeah. So
yes, exactly.
I've never understood the answer to this question, what a morphism of formal topologies should be. And I think there are different answers to this question, and the answer is not clear to everyone. So yeah, like in this, that's a good point. Like in this more extensional setting, we avoid that question.
Yeah, it's completely obvious
Yeah,
what the morphisms should be.
exactly. Yeah,
Um,
and also informal topology. So people use the term formal topology in two different ways. One is for the original notion of formal topology, which is this small set of generators that I mentioned, and the selling point of this is that it is predicatively better behaved. So, for example, this issue with right edge joints and heighting implications, you don't run into that. But then, even then, it's not entirely predicatively well behaved, because the problem of defining the product of two formal topologies, for example, you still suffer from that. And to address that, you need to go to inductively generated formal topology, and that makes it very easy to define the product of two formal topologies. But I think it also introduces this problem that we need to work with. I mean, it complicates the question of what a morphism of formal topologies should be, because now we need to relate two things that are, um, are the generators of this inductive construction of the cover, and then there we lose that.
hmm. Do you think it would
So
be there would be a nice description, like if you translate over the inductively generated formal topology to your setting, whether it be a nice characterization, like an extensional one?
if I translated the inductively, so you mean like a topological characterization of frames that are expressible as inductively generated formal topologies?
Yeah, something like that. Just something more extensional. So,
Um, I don't know, but I know that so formal topologies generalize domains in some way that I don't fully understand. That I mean, I've read many times that the inspiration comes from domain theory and generalizing domains as to obtain a notion that can present a much richer class of spaces. And for domains, I know that there's a topological characterization of spaces that can be defined as spaces of maximal elements of domains. Yeah, spaces that are I think the term used for that is modeled by domains. And there, I think there is a characterization involving. I mean, it's been a long time since I looked at this, but there is a characterization involving Choquet complete spaces, which is it's a complicated notion. But it is completely topological. So maybe if I wanted to do this, maybe I would start with that. But yeah, I don't know I don't know the answer. Like I don't know if anyone has looked deeply into this.
Yeah. I mean, the reason I ask is if you had a good dictionary of sort of going back and forth, then
Yeah,
you would at least have a good target for what a morphism on the formal topology side should be, because you know what it is on the other side,
right. Yeah,
right? So then I mean, it might not give you the answer, but at least you know what it should correspond to, right? So
right. Yeah, exactly.
you have some sort of criterion that
Right.
help.
Yeah.
But your answer makes sense. Yeah.
Mhm.
Are there more questions for Ayberk?
Yeah, I've got a question or two.
Yeah, Dan, please go ahead.
Yeah, thanks for that. That's interesting.
Thank you.
I wanted to ask something. Early on, you mentioned the equivalence between is small being a proposition and univalence.
Yeah.
And one direction's clear, but how do you show that if is small as a proposition, that univalence follows? Is it easy to briefly sketch that?
The details of the proof, I don't remember, to be honest.
Okay. I
Yeah,
forget if
but,
you gave a citation for that.
Tom, so I learned this from type topology, in a corner of type topology, and I think it was due to Martin, and then Tom also worked on it. Tom,
Okay.
Tom can comment more on this,
Yeah. So
on the history of this result.
so you look at the sigma type of y such that y is equivalent to x, right?
Mhm.
And hmm, yeah, okay, I have to think about this as well.
Okay, good. It's not just me
Yeah.
missing something obvious. Okay, it's okay. I can look it up.
And the reference for that is here. I think it was in.
Well, what I do know is it was certainly Martin that proved this. It wasn't me.
Yeah, it
So
was.
at least that
It was
gives me an
Martin,
excuse
right?
why I don't remember.
Yeah, but you generalized it, I think, or something, or maybe I'm
It
misremembering.
would have been a very trivial.
Okay, yeah, this was Martin,
Right.
and
Okay.
this is what is the reference on? Yeah, it's in on small types and union foundations.
Okay,
So
great.
you
Thank
can
you.
look there, and I think that is a pointer to the type topology formalization as well.
Okay, and then another question. You mentioned that if you have a proposition, you can express it as the join of beta of B, where B is false or true, and
Yeah.
beta of B is smaller than P. What that expression? I forget what slide it was on.
It's this one here. This one.
Yeah, yeah. How do you know that?
How do I know this?
Yeah, I mean, this seems a little surprising at first, right?
Yeah, so let's see. If P holds, then we need to show that this join is inhabited. And this we can do because P is, if it holds, it is 1, so it is the top element.
Mhm.
And to go the other way, we have something in this family that is less than P, and that implies P.
Yeah, that's right. Yeah. Okay. Yeah.
So that's yeah. It's actually, I mean, it really seems a bit surprising when you first see this. That you can that hprop has a base like this, but really the trick is that you are using p in the covering family itself.
Yeah. Okay. Thank you.
Just to go back to your question, Dan. Right, so the thing being small tells you that this like sigma y such that x is equivalent to y is a proposition. But if you just take the universes to be the same, then this type is of course contractible. And I think it was already known that that's equivalent to univalence, right? Because sort of the fundamental thing about the identity type is that when you take the total space for one of its fixed is contractible. But when you have this for equivalences, then actually it has to behave like the identity type, if that makes sense.
Oh, I see. So by assumption, it's a proposition, but
Yeah,
it's also inhabited when the universes are the same.
yeah,
So it's contractible. Uh-huh.
right. And then that's already known to sort of be the thing about the identity type, right?
Yeah. Yeah, that's right.
Yeah,
Yeah. Oh,
yeah.
that's
So the
nice.
proof is kind of trivial after all, but you're sort of, I
Yeah, I
think
guess
why
it was a bit confusing because it was stated as an assumption for all U and V, but you only need it
yeah,
for
you have to be careful with the parameters as well.
right. Okay,
Yeah,
thanks.
yeah, my pleasure. Do you have other questions? I just have one more. I think it was slide 17. It's maybe slightly technical, but
Yeah.
right. I guess in this proof you
Maybe
get that.
maybe I know what you're gonna ask. Can you find a similar counterexample that has a small base, or is that the question?
No, I mean, yeah, that's
Because
also interesting, but
that's an interesting question to ask about that as well. But anyways, what was the question?
no. So I was just going to ask. So I think your proof shows that every large, like not stable proposition is small. But I guess it's slightly different from what's in the proposition, right? Which is that the type of all not stable propositions is small.
So I mean, sorry, can you repeat that?
So in your proof, you take a large proposition and then then you show that its double negation is small,
Yeah.
which I guess is saying that not stable propositions are small.
Yes, for U plus and U, that
Yeah,
argument. Mhm.
right. But it doesn't. Does it also tell you that the type of not stable propositions itself is small? I mean, the collection of those things. I guess it
Yeah,
implies that trivially, maybe.
actually, yeah, I think it implies that, but you need to be a bit careful there. I'm not sure because I mean, for omega resizing, if we have propositional UV resizing and VU resizing, we get omega resizing. It should be the same for omega not resizing, right? That, I mean, we have automatically that U small propositions are
Yeah, if you have what
U
we
plus
said,
small.
then yeah.
Yeah. So for U plus and U, I think it gives me that entire omega not is small.
Okay,
I think so,
great.
but this is something that I haven't. Yeah, I mean, when universes are involved, I prefer to write things in Agda, and I haven't done it with that, so maybe, yeah, it
Yeah,
might
sure.
be a subtlety, but
Can relate to the sentiment, definitely. Um, okay. Do you
and
have
yeah, so the
any? Yeah, sorry, go ahead.
and that the other question about this that I mentioned is that I also would like to find a counterexample that has a small base that is large, is small complete, and has a small base and is not locally small. I think that would be much more interesting than this because this one doesn't have a small base. So is it maybe if you have a small base with frames and you have, I mean, it is a small complete, then you can do something clever to always get local smallness or something. Or I don't know if this is possible or not. And I would like to understand that better.
I guess the ordering might be characterizable in terms
Yeah,
of
in
the
many
small
interesting,
bases, right?
yeah, exactly. In many interesting cases, like I mean, algebraicity and so on, it gives us that, right? But then when we don't have these conditions, when we just have a small base, do we need to separately stipulate local smallness? I don't know. I guess that's something that also came up in your investigation of domains.
Ulrich, did you want to
Oh yeah,
comment?
a related question I think might be interesting is to when you have small bases, you have a lifting operation. You can lift a U locale with small base to a V locale with small base when U is a smaller universe than V by taking somehow the joins in V, the V joins of the small base.
Sorry, when V is greater than U, we lift
That's
it.
right.
But then
Yeah.
yeah, that is not going to give us the joins of the families. I think you
have
can do
to
that.
take the V joins using your small base, and then I think you can
when
get
you have,
a V locale,
yeah, I think
and we'll still
that's
have a small base. So this gives you a map from U locales to V locales, and it'll be interesting to prove that that's an embedding. That
right.
if the liftings are equivalent, then you already have an equivalence in the world of U locales.
Right. Yeah.
I think that's true, but it's not. It shouldn't. It might not be too easy to prove.
Yeah. I haven't looked at this with small bases, so that's. I was actually thinking about this in the context of this frame of all nuclei. The difficulties in the context of these difficulties with the frame of all nuclei, because there, I mean, I was trying to find a nucleus that cannot be a nucleus that cannot exist unless some form of resizing holds. And I actually did stumble on something like this, that if you make a copy of the initial frame in the next universe, I mean in the larger category of frames, then you cannot give the small propositions as a sublocale of the large propositions. And this was so I was looking at things like that, and that's when I considered this I mean relationship to the larger frame. But yeah, I haven't yeah, I need to define the lifting operation using the small base. Like I haven't looked at the details of that.
That would also allow you to do.
Good question.
That would also allow you to define things like V maps between U small locales. That would be the V maps between the liftings.
Right.
And then you get more and more maps, but you might not. Hopefully, you don't get more and more equivalences.
Yeah. That's a good point. Yeah, that's something to try.
Okay. Any further questions? Okay. If not, then I suggest we have another silent applause for Ayberk to thank him again.
Thank you very much.
And I hope to well, we hope to see you all in 2 weeks for Astra Kolomatsaya's talk at HoTT. So thank you and take care.
Yeah. Thank you. Bye.